black body radiator is called a black body because it doesn't reflect any energy. Instead, it absorbs all the energy that's incident upon it, and then the atoms re-emit that as visible light. You can see that this brass ball is starting to glow red. Most of the time, things are emitting in the infrared range, but when you get them into a couple thousand degrees, they'll start to glow red. When things glow red, the intensity is pretty low, so that's not a very bright light. As the temperature goes up, the intensity goes up. How bright the light is, actually to the fourth power. That's called Wien's law. So as they studied radiating bodies, they would study how bright they were versus what color they were as the temperature and the frequency increased. So what I'd like to do with this is use a diffraction grating to look at the specific frequencies that are being given off and the brightness of those frequencies. So first of all, you can see that we're starting to get kind of orange right now. Here's what the diffraction grating looks like when you just look at the blue flame. So you can see that we have pretty much a full spectrum there. As you start to get hotter and hotter, you're going to get closer to white light because you have all the different frequencies being given off. This brass ball right now is in the orange region, so we would expect that it's going to be red and oranges and yellows. We'll get it a little bit hotter, and then we'll look at the brass ball with the diffraction grating. So I need to shut the flame off so you don't get any of that. All right, so now, here's looking at just the brass ball with the diffraction grating. And you can see it's no longer giving off light. An incandescent light bulb works by creating enough heat in the filament that the filament will glow. Now you can see that when the temperature is low, it's glowing red and it's not that bright. As the temperature gets hotter, it starts to glow orange. But I still can't crank it fast enough to make it glow yellow like it normally would. Now I have the same light bulb with an AC power source, and you can see that it's much hotter and we're actually glowing white. So if I take the diffraction grating, you can see that a full spectrum is emitted, and the full spectrum is what's giving us the white light. And that probably corresponds to about 6,000 degrees. All right, just for fun, I've also grabbed a little bit higher wattage heat lamp here, and I'll show you the diffraction grating with that. So you can see again that we have a full spectrum, and this has a lot more red in it. Here's a graph of the intensity of some black body radiators versus the peak wavelength that's being given off. Now remember, we've talked about as you get hotter, the peak wavelength is going to be moving further to the left here so that we get a higher and higher frequency. So orange is hotter than red, yellow is hotter than orange. As you start to have all the colors in the spectrum, you're going to glow white. If you glow UV, that means that you're even hotter yet. Well, they started looking at the peak intensity, that's what's on this y-axis here, and they made a prediction that it would be proportional to the temperature to the fourth power, so it's going to be exponential. So like if you look at this first radiator, here's where its peak intensity is. The next one, it's right here. Next one right here. So as we start to graph this, the prediction for this curve is that it would just go up to infinity. Like if you put in energy to get a radiator hot enough, the intensity given off would just keep climbing and climbing and climbing. But the data didn't actually show that. So here's the classical theory over here, what's supposed to be happening. But instead, what happens is the peak comes down as we hit ultraviolet, instead of continuing to be a higher and higher peak. So if you look at this curve that I had drawn, what ends up actually happening is it goes up, but then it comes back down in the ultraviolet range. And that meant that we didn't really understand how atoms work. You can excite an atom by heating it up, and we didn't understand why it wasn't going to give that energy back at the same rate as we got to hotter and hotter temperatures. So what are atoms, and how do they give off energy? That was the question that kind of fueled quantum mechanics. So Max Planck, a German mathematician, tried to explain using a mathematical model how blackbody radiation works. So he knew that light, which is what radiation is given off by vibrations of atoms. So his hypothesis was, what if atoms are not like things in the macro world where they can just have any energy over a continuous array? Anything's allowed, like this ramp. Instead, what if they come in these like discrete bundles called quanta in atoms? Now, he didn't have a reason for predicting that, but it made the math work out for him to say that energy can only come in specific amounts. Nothing in our world works like that. Like a mass on a spring, if it's vibrating, it's going to slow down gradually. It's not going to be like vibrating at 5 times per second, and then all of a sudden it has to jump down to 4, and then jump down to 3, where it can only have certain energies allowed as friction slows it down. It just slows down gradually, continuously. So this is quite a hypothesis to say atoms can only have certain energy. What Planck was saying is that if an atom was, say, at step number 1, you have to give it enough energy by heating it up to get it up to step 2 so that it can radiate that energy back out. If you got it almost up to step 2, but not quite all the way up to step 2, then you did nothing. So there's only specific energies that are allowed for the atom, and they come in these steps. And so then it re-radiates that energy as light, and Planck said we can see this if the energy is proportional to the frequency of light given off times some constant, which he called Planck's constant. So that constant it's a real small number, 6.626 times 10 to the negative 34th joule seconds. If you multiply that by frequency, which is 1 over seconds, you'll get joules. That is the energy of the photons that atoms are giving off, and obviously these steps are very close together because this is a very small constant, but it still is pretty revolutionary that Planck said there's not just any energies allowed, there are only specific energies that are allowed, and it has to come in integer multiples of HF. So n is an integer, so you can be at 1 HF, 2 HF, 3 HF, but you can't be in between. You can never have 2.5 HF. The other thing that Planck said was not all of these modes that the atoms can be in have an equal probability. So some of the higher energy modes are less probable for the atom. It's less likely that the atom can get into that excited state, and that's why we're seeing less intensity given off as we get to the ultraviolet range. That's why it's not following the original prediction that it should just go up to infinity with intensity. So we started to have a little picture of how atoms work, but we didn't know why. All right, one of the main ways that we know that light is a particle is the photoelectric effect. Each particle has an energy of its frequency times Planck's constant. So a higher frequency particle, like UV light, has higher energy. So what the photoelectric effect involves is charging a metal plate by putting electrons on it, which I have this plate of aluminum attached to my pom-pom so you can see that it's become charged. And I could discharge that plate by just touching it and taking those electrons away. But the photoelectric effect discharges the plate by smacking into the electrons with photons. Those photons knock the electrons out of the metal, leaving it uncharged. But you need a high enough energy photon to do that. So if I use my UV light and I shine it on the metal, you can see that I can knock those electrons out of there. And I also made the plate glow a little bit because the UV light was enough to make that phosphorescent paper glow. Green light would not have been sufficient energy to knock the electrons out of the metal. You can see that my green laser pointer is a lot brighter than my purple laser pointer, but the photon energy of an individual photon from green is not as big as the photon energy from purple. So if I put the green laser on this phosphorescent paper, you can see that there's really not much glowing that happens. But when I use the purple laser, you can see that it glows nicely. So let's look at what's happening with the photoelectric effect. And if this seems like it gets kind of confusing, just know that Albert Einstein wrote a paper explaining this in 1905, and that's what he actually won the Nobel Prize for. So if you manage to get this, then you're understanding Einstein. But it does really help us understand how atoms are quantized and how energy in general is quantized if we can understand the photoelectric effect. So in this picture you can see that there's a piece of potassium metal. I didn't have any of that, so I had to use aluminum. When you shine red light, which is the longest wavelength, 700 nanometers, it doesn't have enough energy. The frequency is too low to get any electrons knocked out. When you shine green, that's only 550 nanometers, a little shorter, a little higher frequency, has more energy, and it is able to knock an electron out. And the electron is not going that fast. It looks like, well, that's actually pretty fast, 2.96 times 10 to the fifth. But when you use the purple, which is like 400 nanometers, that electron goes out at 6.22 times 10 to the fifth. So the higher frequency, it takes a certain amount just to knock one out, but then when you get to a higher frequency, you can knock them out moving even faster, which we're gonna see how they measure that. But I wanted you to know that they gave this unit electron volts to each of these different incident wavelengths. So what does that mean? Well, the electron volt is a unit of energy because joules is kind of a lot of energy, and so when you're talking about how much energy a photon has, we really don't want to measure it in joules because you just have a very, very small amount of joules. So energy, we've already said for a photon, is HF. I can say that since C is F times lambda, the energy is also HC over lambda. I just replaced F with C over lambda. Well, when I want to measure energy that way, if I just take Planck's constant, 6.626 times 10 to the negative 34th, multiply it by 3 times 10 to the 8th, and then divide by the wavelength, like 700 nanometers, I'll get energy in joules. But if I want to get energy in electron volts, that is how much energy 1 volt gives to 1 electron. And 1 volt gives 1 electron 1.6 times 10 to the negative 19 joules. That's called 1 electron volt. So if I use this relationship, there's a conversion that we find. If I take the charge of an electron times 1 volt, which is called an electron volt, and set that equal to Hc over lambda, then 1 electron volt is equal to 1240 nanometers. Right, so if light has 1240 nanometer long wavelength, which all of these are shorter than that, it would be 1 electron volt. This purple is about 3 times shorter. It's 400 nanometers, so it has about 3 electron volts. Remember, the shorter you get, the more electron volts you have. Right? But notice that not all of our electron volts went to moving the electron. Some of it actually was used just trying to pry it out of the metal. Hence the red had 1.77, and none of that went to moving the electron because it wasn't even enough to pry it out of the metal. The green had 2.25. It takes 2 electron volts to pry it out of the metal. That's called the work function. So there was only 0.25 left to get that electron moving. Purple had about 1.1 left to get the electron moving. So when a photon comes in, think of it as having energy. Some of the energy gets used just prying out that electron, and then the remaining energy gives the electron its kinetic energy. So here are a bunch of different metals, and you can see that different metals have different amounts of energy needed to get an electron out. So it only is about somewhere around 0.4 times 10 to the 15th hertz, or 4 times 10 to the 14th hertz to get it out of potassium. But zinc takes closer to 1 times 10 to the 15th hertz. So these are called the threshold frequencies, or the minimum frequencies that would knock an electron out of a metal. So I was using aluminum, which was somewhere less than zinc. The work function is the energy it takes. So F0 is the minimum frequency, the work function is the energy that it takes. So all you have to do to turn a frequency into energy is times by H. So if you take H, 6.626 times 10 to the negative 34th, times one of these frequencies, these threshold frequencies, let's say 1 times 10 to the 15th, that will get you the work function in joules. If you want it in electron volts, which you might, just divide it by 1.6 times 10 to the negative 19th, and it'll give it to you in electron volts, which is what we're using for energy on this graph. But what I really wanted to show you with this graph is all these lines are parallel. That's because all of them have a slope of h, right? The energy corresponds directly to the frequency. E equals hf. Now, I'm actually going to use the y equals mx plus b form, where E is equal to m, that's my slope, which is h, x is my frequency, plus the intercept, which is the work function. And that's actually minus because it's got a negative work function. So hf minus the work function, and we already said the work function was f0. So hf minus hf0. All right, that's basically how we interpret these graphs. So this is a picture of the apparatus, and this is called a photocell. So basically you shine light on a piece of metal that's charged. Here we're using a battery to charge it. I just used rabbit fur. The electrons come flying off and they hit this detector, and then we can measure how much current we get. Right? Well, what we're really interested in is how much energy it takes to stop those electrons. So if we have another circuit, we can apply a current in the opposite direction. So we can try to use that current to stop those electrons. And if we stop the electrons with like 3 volts, then we say that took 3 electron volts of energy. It's called the stopping potential. And it is the energy in electron volts needed to stop an electron. The voltage to stop an electron. So a lot of new terms here. We have stopping potential, the work function, the threshold frequency, the incident energy, all those things, basically just to prove that light's a particle with energy hf. So the kinetic energy of the escaping electron is also equal to QV, the stopping potential. Q is the charge of an electron and V is the voltage needed to stop it. So that will get you its energy in joules. And then that is equal to HF minus HF0. And we will do some practice problems with this, but that formula is the general formula for the photoelectric effect. Right, here's one more graph. Shows you that this is the y-intercept work function, the x-intercept threshold frequency, the slope is h, and basically what's happening is we're plotting the energy of the electrons that are knocked out when light is shining as the frequency goes up. So if you hit the metal with green, those electrons are going to leave with some energy. If you hit it with blue, even faster. Red, not leaving at all. UV would be even faster. So the higher the frequency, the higher energy of the leaving electrons. So in summary, light comes in particles called photons with specific energies, h times their frequency, and those photons come from specific energies that atoms can have. So atoms can't just have any energy, they can only have specific energies, and it's the transitions that the atoms are making that give us the photons. So there's jumps that the atoms can make between different energy modes. And not all those energy modes have equal probability. So when things radiate energy, the explanation of blackbody radiation is that atoms must be quantized, that energy must come in specific jumps.